talk about pessimistic algorithms for offline reinforcement learning and offline bandits problems. So my talk is going to have three parts. In the first part, I'm going to quickly review the setting of optimistic algorithms for online bandits. This is just the review of what we saw on Tuesday. There's nothing new here. We'll just quickly take a look at the setup of the problem. We will see why optimistic algorithms are preferred over greedy algorithms for online bandit problems, and then we will take a look at we'll take a quick look at the a theoretical result, and then we will just go over the proof sketch. Again, there's nothing new. We're just quickly going to review the basic setup of the problem, and then in the second part, I'm going to talk about pessimistic algorithms for offline bandits and offline contextual bandits. So first, we'll see the setup of contextual bandit problems, which are a little bit more general than simple multi-armed bandit problems that we saw on Tuesday. And we will discuss about the dataset coverage issue and discuss about why the offline case is more difficult than the online case. And then we will see the LCB algorithms and just quickly review some theoretical results. We're not going to review the proofs here. We won't have time for that. But then after that, I'm going to discuss about pessimistic algorithms for offline reinforcement learning problems, which are again a generalization of the contextual bandit problem. So here, I don't know whether we'll have enough time for going over this section or not. But here I plan to introduce a reinforcement learning problem, introduce the actor critique framework, which is one of the most powerful frameworks for solving reinforcement learning problems, and then we'll discuss about the distribution shift issue, and I will just mention that most of the approaches that are currently being proposed, that have been proposed in the past few years for solving the distribution shift issue, which is the main issue with offline reinforcement learning problems, and most of them fall under the category of heuristic approaches, which manipulate the algorithm in some way by adding some constraint or something like that. But then, since these approaches do not usually present strong theoretical results, we will focus here on a second class of approaches, which are min-max approaches that try to evaluate the worst case performance of policies and then optimize that worst case performance. And then there is a tight connection between these approaches and partial identification approaches in causal inference in the causal inference literature, because the underlying issue in both of these topics is difficulty of performing counterfactual reasoning. So there is a tight connection here. I'm not going to discuss this part today, but if you're interested, I have some discussions in my paper. You can, in my report, you can go over it. So the bandit problem, the simplest version of the online bandits problem, which is online bandits, constitutes of a set of actions and a set of reward distributions associated with each of those actions. So the goal here is to so we have a H period problem, and in each period we just choose an action, collect a reward, and learn something about the environment. So the goal is to maximize the expected total reward that we can obtain in these H periods. So if we know the distribution of rewards, what we can do is to just choose the action which has the largest value of expected reward, and then just repeat choosing that action over the entire H period. So the reward that we can collect is going to be H times expected value of the maximum reward. But we don't know the distributions in practice, so we do is to use the information that we collect over time for making the decision at each time period. We have seen these topics, so I'm going to just quickly go over them. I'm not gonna spend that much time here. So usually we work with regret instead of the expected reward. So the regret is just the optimum, the maximum reward that we could have collected minus the reward that we have actually collected using our policy. We have action gap, which is the gap between the expected rewards of the optimal action and the action that we have chosen. We have regret decomposition theorem that we saw on Tuesday, so we can just represent this regret in terms of the summation of our actions of the action gaps, so optimality gap of action times the expected number of times that we choose that action. So a greedy strategy, we discussed on Tuesday that the greedy strategy is not the best strategy that we can follow here, because first of all, in the greedy strategy, what we will do is to calculate the expected value of rewards that we can that we have collected so far by pulling arm A, and just maximize at time point t, just maximize the expected reward up to time point t minus 1. But the problem with that approach is that let's say we have just let's say we have like 5 arms here, and based on the samples that we have collected, we have constructed like mean values and confidence intervals around those mean values for each of these actions. But in if you just simply follow the greedy algorithm, if you just simply follow the best empirical arm approach, what can happen here is that it might be the case that these are not true values, right? These are the like intervals based on the sample averages that we have actually collected so far from each arm. So it might be the case that if we simply choose the arm with the largest value of mean, it might be the case that there is another arm that basically has a slightly smaller mean value, but it has a much larger uncertainty. So if we simply choose this guy, then for the reward of this arm might be larger than what we have observed here for the mean value. So we will we may be actually performing suboptimally. So since we have the opportunity of performing exploration, since we can actually learn more about arms if you want, kind of reasonable strategy would be here to follow the to use the upper confidence bound instead of the mean values. So in that way, if you choose an arm with choose an arm which has a large upper confidence bound, then that arm either has a large true mean value, which is good actually, or it has a high level of uncertainty. So we can just if you choose that arm, we can reduce the level of uncertainty by pulling the arm and learning about its actual performance. So in the upper confidence bound algorithm, what we do is to add a bias term to the mean rewards, and that bias term is proportional to 1 over root n. Is proportional to the standard deviation of these sample means. But the constant that is chosen that we can choose for here, it can vary. In this case, what we're doing is to define the bound that define the bias term as root 2 log 1 over delta over n, which is where n is the number of times that we have pulled this guy. So we just calculate these upper confidence bounds and maximize it over the set of actions. Here we have the theoretical result that we saw on Tuesday. Again, I'm not going to go through the details here, just to remind you what the result is. We have the theorem that says if we set delta to be equal to 1 over h squared and assume that the rewards are one sub-Gaussian, then the regret is going to be upper bounded by 3 times summation of action gaps plus 16 log h times summation of 1 over action gaps. In the proof, again, I'm not going to go over details here, but in the proofs we generally saw that we can bound this guy. We can bound the expected number of times that we have pulled each of these arms, because the regret decomposition allows us then to convert our result to what we have here. So all we need to do is to just bound this guy, and then for this purpose we define a good event in which the true mean of mu1 is smaller than its upper confidence bound levels. And for action A, which is actually this guy is defined for each action specifically. For action A, these terms, which are like similar to the defined in a similar way to the upper confidence bound, these guys are smaller than this term specifically is smaller than the true reward of the best arm mu1, and we showed that this event happens with high probability. Its complement happens with low probability. And we show that under this event, the total number of times is bounded by the value of UA that we choose here. So then we can easily just decompose this guy and upper bound it using these 2 theorems that we have here. I'm going to skip the details here and jump to the offline case, which is the focus of our discussion today. So in the offline case, we will the main setup that we'll see here is the case of contextual bandits. So in the in the multi-arm bandits problem, the simple multi-arm bandit problem that we just saw, we had an action, and based on that action, we were collecting a reward. But here in the contextual bandits problem, the environment has a state as well. And based on that state, we choose our action, and based on state and action, we just collect some reward. So we have a set of state, a set of actions, and a random reward. The state is assumed to be exogenous, meaning that we do not control the state. We just arrive and there is some state over there, and we just look at the state and make our decision. And next time that we are making a decision, the environment doesn't have any history, so that state just resets, and it comes, we are assuming that it comes from a certain distribution row. So we are assuming that the evaluation policy pi is deterministic, meaning that we look at the environment state and just choose one action. There's no like distribution over the actions, but since we're working in the offline case, we are assuming that we have a data set. We do not have an opportunity for exploration. So we have a fixed data set, and that data set comes from a behavior policy, which is a stochastic policy, meaning that for each state, we have like a distribution over the set of states. It might be the case that like the data set has been collected using like several different deterministic policies, but anyway, we're assuming that the policy that generates actions for each certain state for this data set, it's a stochastic policy, and we are denoting the distribution, the joint distribution of states and actions for this data set by mu. So you can decompose mu as the distribution of actions given states times the marginal of states. So basically, the distribution of actions given states is this behavior policy that I just mentioned, and the marginal of states, it can be equal. I mean, we can assume that it's equal to this row, but it might be also different because this is the marginal distribution of states for the training, and this is the marginal distribution of states for the evaluation or testing phase. They might be different. So here we are assuming that these two distributions are like distinct, and they denote this guy by mu. So we have the reward of this contextual multi-arm bandit problem being defined as R of S and like pi of S. So here we do not have sequential exploration. So I mean, since the data set is fixed, we only make the decision once. And for state S, we just choose pi S and we collect some reward. So the regret is defined as the difference between the optimal reward that we can collect in state S and the reward that we have actually collected following our policy. And the expected value of regret will be our like objective function. So here we have expectation over both the initial state S and the data set that we have here, D. So this is the main paper that I'm using for our today's discussion, specifically for dataset coverage part. Why is this problem difficult? What is the issue with this model? Why is it more difficult than the online case? So the key issue here is that the behavior policy that has generated our dataset, it might be different from the evaluation policy that basically we're trying to use for our choosing the best policy. So this guy is actually not a distribution, but the term distribution shift comes from general cases in which the evaluation policy can be stochastic as well. But anyway, that's the key issue, and the problem with this setting is that if we have a data set in which in a certain state, in all or in most of the samples, what we observe is that in this state we choose to move forward. And then we have an evaluation policy. We're trying to evaluate the performance of a policy in which, in this state, we want to like choose the action of turning left. Then evaluating this policy is actually a difficult problem. So we have a problem of counterfactual queries here, and it might create severe issues in safety critical applications, specifically like healthcare decision making or autonomous driving or things like that, in which if we just look at a fixed data set and make some decision based on the data set, and the decision turns out to like perform poorly because we are not able to accurately evaluate the effect of that decision, then it might create serious issues. So let's think a little bit about the dataset composition specifically. So here we have a range of possible dataset compositions that we can have. On one end of this interval, we have uniform coverage, meaning that the dataset that we have, for each given state, it has like the distribution of actions that we have in our dataset is a uniform distribution. And on the other end, we have expert data. So in expert data for each given state, we almost all of our samples are collected from the optimal policy, right? So there is a like I mean, we have like very few samples from suboptimal actions. If you have a uniform coverage, then best empirical arm would be the best approach. So we just calculate the average of rewards for any given state. We just calculate the average of rewards for each action, and then use those mean rewards for making the decision. And it's going to perform well. It can be shown that it performs well, both empirically and theoretically. And if you have an expert data set, usually imitation learning approaches work better. Imitation learning means that you just look at the most frequent arm and pull that arm, because we may have like a couple of samples that for a given state, we may have a couple of samples of suboptimal action that just by chance have a like high value of reward. But if we know that we are in an expert data setting, then we prefer to pull. Then we prefer to choose the most frequent arm strategy. But I mean, in these two extreme cases, we know what to do. But in practice, what happens is that we usually, the data that we have usually fall somewhere in between this range, right? And in that case, we are usually interested in naturally, I mean, interested in balancing between these two terms. Naturally, we're interested in balancing between the mean reward value that we have estimated using our data set and the number of samples that we have. We need to kind of balance between these two, right? So here we're trying to kind of quantify the data set decomposition. We're trying to have some sense about where our data set is located in this range. I mean, this is not the only way to like think about data set decomposition, but it helps us to understand what is the effect of our data set on the policy evaluation. So here we have the occupancy measure being defined as the joint distribution of states and actions. So we have a two-dimensional space, we have state on one dimension, we have action on the other dimension. The joint distribution of states and actions is actually defined here as occupancy measure. So in the case of contextual bandits, we can decompose this distribution as the conditional of A given S, which is an indicator function, because we are assuming that we have a deterministic policy. So for each state, we just choose one action, and then times the marginal of state. The occupancy measure can be defined in more general cases in which, like reinforcement learning, in which the distribution becomes more complicated and the policy might not be, stochastic. But here we're focusing only on the case of contextual bandits. So the concentrability coefficient, which is a measure of where we are located in this range, is defined as the norm infinity of the ratio of the occupancy measure associated with our policy pi divided by the joint distribution of our data set. So we just look at the values of D and mu at a certain pair of S and A, and just take the ratio and just take the maximum of the ratio over all the space. And here we can just simplify this guy and write it down as rho S, and we can easily check that we can write it down as rho S divided by mu of S and pi S, the norm infinity of this guy, which is the maximum of this ratio over all the possible values of S. So there are two commonly used versions of this definition. One of them is the maximum of this ratio over all the possible policies. Over all the possible policies, it's usually a large number, and there is another version which takes this ratio, calculates this ratio for the optimal policy. So we just compare our concentrability coefficient with the distribution. We just compare our behavior data set, our fixed data set, with the distribution that is generated by the optimal policy. So here, for the simple case of multi-arm bandits, we can easily check that this guy simplifies even more. I mean, if the number of states is equal to 1, we have a very basic case of multi-arm bandits, simple multi-arm bandits. This guy simplifies, so we have only one state. This guy becomes 1 over mu of A star. So if C star is large, it means that most of our samples are generated from the expert policy. So we're getting closer to this guy. And C star is always, if C star is small, if C star is small, it means that mu of A star is large. So most of our samples are generated by the optimal policy. And C star is always greater than or equal to 1. You can easily check this because this is a ratio of two densities. So they both sum to 1. So the ratio of one of them over the other one is actually lower bounded by 1. So here we have a kind of algorithm which tries to do that balance between So the reason that I mentioned the notion of concentrability coefficient is that it shows up in the theoretical analysis of the LCB algorithm that we'll see in the next slide. So the one approach for kind of balancing between these two guys is to use the reward penalization approach. So what we do is to calculate the reward, like estimate the reward using the samples that we have in our data set, and penalize the reward based on the number of samples that we have. So a natural choice here would be to define the penalty term proportional to 1 over root n, which is like proportional to the standard deviation of these confidence bounds. And you can see that in this case, if we do that, so first of all, the reason that we are doing this reward penalization is that you can consider cases like this in which we have one action which is like slightly, which on average performs slightly worse than another action, but it has much lower variance, much lower uncertainty. So if we choose this action, since we do not have any opportunity for performing further exploration, what might happen in practice is that this guy may perform poorly, and we may incur huge costs. So we prefer here to be conservative, to be risk averse, and choose actions for which the uncertainty levels are smaller. I mean, even if they have like slightly worse performance, we prefer to choose actions that have slightly that have better uncertainty levels. So here in this paper that we are reviewing, the penalty term is defined in this way, and in the SB algorithm we just perform a policy evaluation, and then in the policy optimization phase we just maximize our for a given state, we just maximize the lower confidence bound that we have constructed here. Here we have some theoretical results for the LCB algorithm. We'll just see the results. We're not going to go over the proofs since we don't have any time. So here we have the results for the simplest case in which the number of states is equal to 1. This is a simple multi-arm bandit problem. Here we have a result on the expected regret. So if n is large enough, such that n over log n is greater than 8 C star. C star is the concentrability coefficient of the data set that I just discussed about. And if you choose delta to be equal to 1 over n, delta is what we have here. So in our penalty term, if you choose delta to be 1 over n, then the expected regret, this expectation is over the data set. We don't have any states here, so the expectation is only calculated over the data set. If we take the expectation of the regret, or suboptimality between the optimal action and the action that the LCB algorithm chooses, then we can show that the expected regret is overbounded by a factor of root C star over n, and I mean up to a factor of log n. And then we have an information theoretic lower bound. So we have a like worst case performance result for any arbitrary policy. So we have a class of bandits with the concentrability coefficient being at least as good as C star. And then for this class, we show that if we calculate the worst case performance of a certain action over this class and like optimize that worst case performance, then it's going to be lower bounded by a factor of root C star over n. And this holds only if C star is larger than 2. C star being larger than 2 in this case means that means that mu of A star being smaller than half. Mu of A star being smaller than half means that we are like at least we have at least some distance from the expert data set, so we're not like in the expert data mode. So this actually shows that if the data set is not close to expert data sets, then the LCB algorithm kind of achieves this rate up to some factors. And if mu of A star is larger, it's closer to 1, meaning that the data set is closer to the expert data. Then in that case, authors show that the imitation learning approach, the most frequent pooled arm, it achieves an exponential rate decay, so it performs better actually. And for the case that we have more than 2 states, the authors show that basically we have a similar upper bound here for the expected regret. So your expectation of regret is calculated with respect to both the data set and the initial state and actually state distribution S, and then they show that the rate in this case will be proportional to root C star minus 1 over n plus 1 over n. And it means that basically if C star is close to 1, if it's small, the convergence rate is going to be 1 over n, and then if C star, as C star increases, the rate converges mostly to 1 over root n. And then similarly here, we have a information theoretic lower bound, which says that, again, if we define the family of contextual bandits in this way, in a way that they have smaller, in a way that they have a concentrability coefficient of at least as good as C star, and take the worst case performance over this family and calculate the infimum over all the policies for this family, then it's going to be lower bounded by a similar rate, which means that the LCB algorithm is actually able to achieve this rate. So yeah, like I think 5 minutes, and I have a discussion for the more general case of reinforcement learning here, which I think will take like 15 minutes. So I don't know whether you prefer to like go over this case, go over the more general case, because here we need to set up the problem first. I don't know whether you're familiar with the reinforcement learning or not, but here we need to like discuss about some basic stuff before going over the method that we want to talk about. If you prefer me to go back and like discuss about simpler cases like the proof of the online case, or I don't know if you have any questions for the simpler cases, we can go back to those cases. And if you wanna, if you're interested to hear about the reinforcement learning case, we can discuss about it. I don't know. Do you have any suggestions?
How long does it take for you to?
I think it will take 15 minutes because we need to talk about the basic setup of the problem. We need to understand what we're talking about. If people have taken like 231B, they probably know the reinforcement learning setup, but I'm not sure whether everyone is familiar with the basics. So I need to introduce what the Markov decision process is, and then talk a little bit about the actor critique framework, and then discuss about this approach. Which, I mean, the core idea is that we want to see how this concept of pessimism can be incorporated into the actor critique framework, which is a reinforcement learning approach. So the problem is more complicated. It involves like a multi-period problem. We have a feedback loop here, right? So the core idea that I want to discuss here is that how we can incorporate that approach into like more complicated models. I mean, if you're interested, we can talk about it, but I mean, that it's just a generalization of what we saw so
far. Okay. Maybe let's see if people have questions.
Okay.
Parts. Anyone has questions? Maybe let me ask a question and see how, like, so can you go back to the results that you like, or the LCB algorithm that you mentioned? So the setting seems to be in this like offline setting. It's more like an estimation problem. I wonder, for example, if you like select the arm with the best empirical average, is there any result for that? Do you really need to like account for the lower?
Yeah. I need to check. I'm not sure. I think there are some results for the suboptimality of the best empirical arm as well, but I mean, I don't have the results at the moment. I need to check.
The thing is, like the 1 over square root n is like how you can estimate like a general parameter, right? So if you ignore like the CS star, maybe the constants, then up to like 1 over root n, you probably can still like prove a bound that's like bounded by O of 1 over root n, or log n, let's say, times the action space time. The question is like how much. Maybe if you like, I don't know, have you seen like, do they really like discuss the advantage of this confidence? Like, yeah,
I see your point. I need to go over the paper again, actually. I'm not sure whether they had that discussion, but yeah, that's a very good point. I'll check that.
Okay, sounds good. And then one more question about, like you said, the distribution shift. Is it like these results are assumed? So there is this pi. Can you go back to the setup? so there's the evaluation policy, and then pi star is the like the minimizer, right? Is that?
Yeah.
So the evaluation policy here is just like a dummy variable, right? So you just minimize over that, right?
Yeah, exactly. Here we have the distribution over the actions, but the evaluation policy is just one action for each state.
Yeah, but then pi star is like
pi star is just one action, right?
Not one action, like the optimal policy, right? Is that?
Yeah, I know. I mean, but the optimal policy is just one action. It's not a distribution. That's what I mean.
That's fine. Yeah. So what I'm trying to say is, so the expectation here, like that you, so when you say minimize regret, so it's not clear where this behavior policy comes in. Is that because you're doing the population level expectation?
Yeah. So the behavior policy is what has generated the data set, right? So you have expectation over the data set, and what you estimate here, this pi s, I mean, pi star is just your optimal action, right? But you want to optimize it using an estimator. I mean, maybe my notation is not appropriate here, but here we have an estimator, and that estimator is generated based on the data set, and that data set is generated by behavior policy. Is that clear?
But the expectation is not under the, when you say the expectation is under the first expectation, is it like under the true data? Is there like the true, let's say there is a true policy, like the, not the true policy, but what I'm trying to say is that the first expectation is it under the same. So you're saying the data is generated from the data. When you have the data, then the expectation is not. Is it an empirical expectation? Is it like you've also take the expectation over D as well?
Yeah, we are taking expectation over D. So what we are doing here is to say that, okay, we have a data set, which is, I mean, there are some reward distributions, right? We are assuming that we have a true reward distribution. And then for that reward distribution, we have some policy. Let's say the policy is just, let's say the behavior policy is deterministic as well. So for each state, there is some certain action, right? We have a policy.
Sorry, let me understand. So this mu is like the joint distribution. So where does the mu like come in? So this mu is related to that behavior policy. Is that?
Yeah, exactly. I think I briefly explained it, but let me just explain it again. So this mu is a joint distribution of states and actions, right? So you can break this distribution as action given state times the marginal of state, right? Action given state is what exactly we have here. This behavior policy.
Okay.
Yeah. This pi beta is our action given state, and this is the marginal of state. If you assume that the state of the state distribution of the environment is not changing from the training phase to the test phase, I mean, it's the same in both of them. You can just replace this row here, so you can just write down mu as the distribution of pi beta times rho. So everything will simplify, but I mean the concentrability coefficient and everything will simplify. But here I'm just considering a more general case.
More general case being that rho.
More general case meaning that we can have some rho beta that has generated this guy, right? That say this because we only have a so we have a single period problem, right? We just arrive, there is some state, and we make our decision based on that state and collect some reward. But that state distribution, it can change, right? I mean, in the behavior, in the training phase, we are collecting this data, we might have like a different state distribution, but in the test phase, the state distribution can change, you know, these two can be different.
Okay, but that pi beta is the same in both cases.
Pi beta is the same. Pi beta is the same. I mean, pi beta is only plays a role in the training phase.
Okay, and then this pi star is like computed under the which row, the true, like there's like there could be like two different rows, right? At the test.
Pi star doesn't depend on the data set, right? Pi star doesn't depend on the data set at all because it only depends on the reward distribution that we have, and reward distribution is fixed. Right, so you have a reward distribution. Given that you have your certain state, you just calculate your optimal state. I mean, the state which has
it doesn't depend on the distribution of the states, does it?
Yeah, it depends, but I mean, the policy is defined as a function of a state, right? So you have a state, and this pi is a function from state to a set of states to a set of actions.
Okay, but like when I want to compute the optimal policy, how do I compute the optimal policy?
Okay, you can conditional your state, right?
Okay.
And conditional on your state, you just look at your environment, and conditional on the state of the environment, you just choose the action that has the largest
So
reward.
you have to take the expectation condition like of the like RSA conditional on the state. Like so it would be the conditional distribution of A given S involved in it, right?
Yeah, exactly. Then this row is actually what is doing the job.
Okay,
right?
so that row is the like the so
the evaluation distribution.
Okay, so that's the okay. But then the test, you're saying that the training data could have a different row. That's what you're saying.
Yeah. I'm assuming that data could have been generated because I mean the way these data sets are in practice generated is like multiple policies. I mean people run different policies and you just collect the data sets and combine them. Right?
Okay. I understand. So now the result that you presented, like, is it like, does it consider this shift? Is there anywhere in this result that the shift comes in?
The way that we define the concentrability coefficient, you can when I said that everything will simplify if those two guys are the same, it means that the concentrability coefficient here simplifies, right? So if you assume that those guys are the same, this guy just you can decompose it and it becomes 1/5.
Okay, but in practice, like d pi could depend on the test row. Is that?
Yeah.
Is that okay?
Yeah.
Okay, thank you.